So students, there is one more topic in second paragraph of your syllabus. So that is regarding boundary layer. So okay. So to understand the concept of boundary layer, so I consider one plate. So this is one plate. Now this is a stationary plate and the liquid is flowing. Say water is flowing above this plate with uniform velocity capital U. Okay. Now the layer of fluid which is adjacent to the plate. Now this is the plate. Okay. So there is formation of some thickness of fluid where something going on in that particular layer. So the layer which is adjacent to this plate that we call as the boundary layer. Okay. So within that layer, what happens? So that layer changes its characteristics something like this. So you can say it changes its thickness something like this. You can see along this curve. Okay. Something like this. So this edge of this plate that we call as leading edge, and the other end of the plate that we call as trailing edge. Okay, so this is a flat plate. Now within this flow near to the boundary, what happens? There is a formation of one layer whose thickness varies from leading edge to trailing edge of that plate. So within the initial part, so this is the initial part of this layer. Okay, so that we call as laminar boundary layer. Laminar boundary layer. Okay, the end part of this layer we call as turbulent boundary layer. Okay, so in between these two layers, we have the boundary layer in transition. Okay, that is the boundary layer in transition. So if now I try to define the boundary layer, the definition is something like the layer of fluid adjacent to the boundary is known as boundary layer. Okay, so normally you can say the boundary layer is formed whenever there is relative motion between the boundary and the fluid. Okay, so boundary layer exists only when there is a relative motion between the fluid and the boundary, between the boundary and the fluid. Now the boundary here is the boundary of the plate. So that is stationary and fluid is moving above this plate. So there is a formation of boundary layer. Okay. So when there is a relative motion between the boundary and the fluid, then there is a existence of shear resistance or viscous force. So there is a presence of shear resistance between the layers of the fluid. Okay. So above this plate, you can say the liquid is flowing with the uniform velocity u. So adjacent to plate, there is a formation of one layer that we call as boundary layer. Now, if I try to write some important points regarding this formation of boundary layer, okay, the first important point, or you can say the silent features of this boundary layer, the first important point is the edge facing the direction of flow that we call as leading edge. So the edge facing, yeah, you can say the edge that is on the rear side of the plate that we call as trailing edge. So near to the leading edge, so you can note it down, near to the leading edge of the flat plate, the layer, or you can say the boundary layer, is laminar. That is completely laminar. Okay, so you can say the velocity distribution within that part is purely parabolic in nature. That is parabolic in nature. So that is within the first part of the boundary layer. So this is the first part that is here. Okay, so the flow is laminar and the velocity distribution is parabolic in nature. The point two is the thickness of boundary layer increases with distance from the leading edge. Now the distance of boundary layer, or you can say the thickness of boundary layer is noted by delta, and it goes on increasing when we move from leading edge to trailing edge. Okay, so this thickness of boundary layer goes on increasing as you see in this diagram. Okay, now this thickness is along the y direction of the plate, along the vertical direction of that plate. Okay, so third point here you can note down, for a turbulent flow. Okay, so you can say uh, within this region of boundary layer, so there is a one part of boundary layer where the flow is turbulent, and that part of boundary layer we call as turbulent boundary layer. Okay, so for a turbulent boundary layer, a very thin layer is there in which further the flow is laminar. Okay, so you can see this part of the boundary layer, the flow is turbulent, and this boundary that is shown in yellow color is the turbulent boundary layer. So within this boundary layer, we have a part that is adjacent to the plate where the flow is again laminar. Okay, so this part of boundary layer, this thickness of boundary layer, this we call as laminar sublayer. Okay, so the laminar sublayer is a small layer within the turbulent boundary layer where the flow remains laminar. Okay, that is another important characteristic of boundary layer. Then another point you can note here, the velocity distribution in turbulent boundary layer. Okay, so you have turbulent boundary layer. So within turbulent boundary layer, the velocity distribution, so that is not parabolic in nature, so that obeys, that velocity distribution is given by log law. Okay, or you can say that is given by 1/7 1/7 power law. Okay, so we see further uh, in the coming topics. So what is the meaning of 1/7 power law? This is the how velocity varies within the turbulent flow. The velocity relationship with respect to there is a relationship between u and y. So that is in the form of uh, logarithmic nature. Okay, for turbulent flow, that variation is in the form of logarithmic nature. Okay, so another point you can note here, delta. So this delta increases as we move from leading edge to trailing edge. However, this delta decreases when we increase the value of u. Okay, so you can see in this diagram, if I increase this u, okay, so in that case, this thickness comes to lower side, something like this. Okay, so as we increase the u, so delta decreases. Okay, another point you can note here, delta increases as the kinematic viscosity, so nu is the kinematic viscosity increases. Okay, if the viscosity of fluid increases, the kinematic viscosity of fluid increases, you have more value of boundary layer thickness, delta. Okay. Another point. Now we have factor ux by nu. Okay. Now if this factor is less than 5 into 10 raised to power 5, the boundary layer is laminar. Okay, and their velocity distribution is parabolic. Okay, so if this factor is greater than 7 into 10 raised to power 5, the boundary layer is turbulent. Okay, and the velocity distribution is given by power law, that is 1 by 7th power law. Okay, so these are some important characteristics of this boundary layer. Okay, now we see how we measure the boundary layer thickness. Now this one is the boundary layer thickness, so that we call as delta. Now we see how we measure this value of delta. So next is boundary layer thickness. Okay. Now to define the boundary layer thickness, we have a definition. So that definition is the thickness of boundary layer is defined as, so delta is defined as that distance from the boundary, that is the boundary of the plate, in which the velocity reaches 99% of the velocity of free stream. So that means U should be equal to 0.99 times of capital U. Now what is the meaning of this? Now you can see here in this diagram. So you have a plate, some liquid is flowing above the plate. Okay. Now the velocity, say if I see the laminar part, if I see the laminar part of this boundary layer, if I move in the vertical direction, so what happened? Velocity of this layer is almost zero. As we move in the upward direction, the velocity goes on increasing. Okay. Now this variation is parabolic in nature. Okay. It increases from 0 to, now when I cross the boundary, that is the red part, so here the velocity of layer is capital U. Okay. So velocity along y direction changes from 0 to almost U. So that thickness of layer for which the velocity reaches 99% of the velocity of free stream, that thickness we call as the thickness of boundary layer. So this is the thickness of boundary layer at some distance x from the leading edge. Okay. Now, this you keep in your mind that this definition is gives us the approximate value of boundary layer thickness. That is not the exact value. This gives us some idea of that thickness. So this is the one approximate value of boundary layer. Okay. So for greater accuracy, we have to adopt some other definitions of boundary layer thickness. So for more accuracy, we have three different definitions for boundary layer thickness. Okay. The one is the one is called the one is called displacement thickness. Okay, that we represented by delta star. The second one is momentum thickness. That is theta. And third one is energy thickness. That we represented by delta E. Now we see the first definition, that is displacement thickness, that is delta star. Now what is the meaning of this? Now if I write the definition of displacement thickness, so it is the distance measured, it is the distance measured perpendicular to the boundary by which the free stream is displaced on account of formation of boundary layer. Now the meaning of this definition you can see in next lines. Now let us say we have this plate. This plate is the stationary plate. So of this plate there is a formation of boundary layer. Okay, and there is a flow with velocity capital U. Okay, now I consider this part, say here. So within the boundary layer, the variation is parabolic in nature. The velocity variation is parabolic in nature. And beyond this, the velocity of stream is almost U. So we can call this as delta, that is the boundary layer thickness. Now I consider some very small part of this flow, which is at distance y from the plate, and the thickness is dy. Now let us say this plate has unit width in the plane perpendicular to your screen. Okay, so you have unit width of this plate perpendicular to the screen. So let us say rho be the density of flowing fluid. That fluid is flowing above this plate. The rho be the density. Okay, so now you can write the mass flow per second through small strip. mass flow per second through this small strip. So mass flow I can write as rho into area into velocity. Okay, so rho is the density of the fluid, area is so through this small strip, the area is dy into 1. Okay, and the velocity is, now say here the velocity of layer is small u, is u. Okay, now I again write, now this becomes rho u dy. Now again write the mass flow per second through small strip. Okay, if this plate is not there, if this plate is not there, then what happen? The flow, the velocity of stream is same as u. Okay, if you consider the same strip, the flow velocity is u, so you can write this mass flow rate as rho into u into dy. So u is the capital U. Okay, if there is no plate, the mass flow rate is rho u dy. So now what happens? With the presence of this plate, there is a reduction of mass flow rate. So next you can write the reduction of mass flow rate is equal to the difference of these two. So rho u minus small u into dy. So here the term u minus u, that we also call as uh, velocity defect or velocity defect. Okay. Now you can write the total reduction. Total reduction of mass flow rate. So total reduction of mass flow rate is the integration of this term when y varies from 0 to delta. So I can write it as the integration of rho u minus u dy. So variation of y is from 0 to delta, and this is my equation number 1. Okay. So let we have a situation now. So we have this plate, liquid is flowing above this plate. So now what I do, I displace this plate in the upward direction by a distance delta star. Okay, by a distance delta star. So this distance delta star is the distance up to where the velocity becomes 99% of u. So in the direction of delta star, in the direction of this y, your velocity varies from u to total u. Sorry, 0 to capital U. Okay, so delta star, that distance is the distance from the plate to the free stream velocity, where that free stream velocity becomes capital U. Okay, so when I move this plate in the upward direction, so there is again reduction of mass flow rate. So that reduction I can write as, so I can write the reduction or the loss of mass flow rate with the movement of this plate in the y direction by distance delta star. Okay, so that is equal to rho u delta star. So again, this is the loss of mass flow rate. So now you can see the equation 1 is equal to equation 2 because both are the mass flow rate due to the presence of this plate or due to the movement of that plate. So I equate 1 with 2. So I can write rho u delta star should be equal to integration of 0 to delta rho u minus small u into dy. So now I rearrange the terms and I can write delta star is equal to integration of 1 minus u divided by capital U dy, and y varies from 0 to delta. So this is the formula that gives us the displacement thickness. So with the help of this formula, I can calculate the displacement thickness. So displacement thickness means uh, the movement. You can see now the definition. It is the distance measured perpendicular to the boundary by which free stream is displaced on account of the formation of boundary layer. Okay, so that is delta star. Okay, so this is the distance by which we move the plate, by which we move the plate on account of formation of boundary layer. Okay, so this is displacement thickness. Now the next one is the momentum thickness. So that is theta. Okay, so if I write the definition, so it is the distance measured perpendicular to the boundary of the plate by which the boundary should be displaced to compensate for reduction in momentum of the flowing fluid on account of boundary layer formation. Okay, so in momentum thickness, we consider the loss of momentum due to the formation of boundary layer. Sorry, due to the formation of boundary layer. Okay, so you have a flowing stream. Okay, so for flowing stream, we have some momentum. If we flow that stream above a plate, plate is there, there is a formation of boundary layer. So According to that plate, according to that formation of boundary layer, there is a loss of momentum. Okay, so that loss ultimately gives us the thickness. So that thickness we represent as the momentum thickness. Okay, that we represent as momentum thickness. Now in this you can see, I can write again the mass flow rate through the same elementary strip. Okay, so that is rho u dy. So you have a plate at the bottom, you have strip at distance y, thickness dy. Okay, so now you can write its momentum. Okay, so momentum you can write it as, so multiply this by u, so that comes out to be rho u square dy. Okay, so this is the momentum of fluid when it is in boundary layer. Now I can write again the momentum of the same mass before entering the boundary layer. Okay, so before entering the boundary layer, the velocity of that layer is same as capital U, that is other than that of small u, that is capital U. Okay, so that momentum I can write here, the mass into the capital U is that velocity. So this comes out to be rho small u into capital U dy. Okay, so this loss of momentum when fluid enters to the boundary layer, so this loss of momentum I can write as rho u u dy minus rho u square dy. So this becomes rho u into u minus small u dy, or total loss of momentum. So that comes out to be the integration of rho u minus u dy, and y varies from 0 to delta. So this is equation number 1. Okay. So now I again consider theta instead of delta star. Now I consider theta. So now I consider theta. Okay. So theta be the distance by which plate is displaced when fluid is flowing with a constant velocity u. So theta is the distance by which I move this plate in the upward direction to the layer where velocity is u. Okay. So I write this theta. So theta is the distance by which plate is displaced when the fluid flowing with a velocity capital U. Okay, so now I can write the momentum. So first you write the mass loss, that is the mass flow rate loss, or loss of, I write it as loss of mass flow rate by the movement of plate by distance theta. So that loss is, so the mass is rho theta into u. Okay. And the momentum, loss of momentum, that is rho theta into u. So that becomes rho theta u square. That is your equation number 2. So now equate equation 2 with equation number 1. So rho theta u square is equal to rho u minus u dy. Theta varies from 0 to delta. So from here you can calculate theta, that is small u upon capital U, 1 minus u upon capital U into dy. Theta varies, y varies from 0 to delta. This is the formula for momentum thickness. Okay. So on the same lines, you can write the energy thickness. So energy thickness is delta E. So if I write its definition, it is defined as the distance measured perpendicular to the boundary of the plate by which the boundary should be displaced to compensate for the reduction in kinetic energy of the flowing fluid on account of boundary layer formation. Okay, so in energy thickness, we consider the loss of kinetic energy by the formation of boundary layer. So that concept we use in determining the formula for energy thickness. Okay, so now I again write the mass flow rate through strip. So that is rho u dy. Okay, now I can write the kinetic energy of same fluid. Okay, inside the boundary layer. So that is half into mass into its velocity square. So that becomes equal to 1 by 2. Mass is rho u dy into u square. Okay, so now again I can write the kinetic energy of same fluid before entering the boundary layer. So that is equal to half into mass into the velocity of layer. Now before the boundary layer, the velocity is capital U. So half into mass into velocity square. So now you can write the loss of kinetic energy, okay, through strip, that is equal to 1 by 2 rho u dy into u square minus 1 by 2 rho u dy into u square. and this is equal to 1 by 2 rho u into u square minus small u square into dy. So now you can write total loss of kinetic energy, that is the integration of 1 by 2 rho u square minus u square dy. Y varies from 0 to delta. That is equation number 1. Okay. Now say we have delta E distance. Now I move my plate by this distance. So this is the distance delta E by which the plate is displaced to compensate for reduction of kinetic energy. Okay, so I move my plate from its original position to distance delta E. When I move the plate by distance delta E, the mass is uh, the mass is rho u into delta E, and then its kinetic energy half mass into velocity square. So this is your equation number 2. So I equate equation 1 with 2 again. So that is 1 by 2 delta E u square equal to 0 to delta 1 by 2 rho u square minus small u square dy. So now from here I can write delta E. So that should be equal to u upon capital U 1 minus u square upon capital U square into dy integration 0 to delta. So this is the formula for energy thickness. Okay, so these are the 3 accurate formulas for determining the boundary layer thickness. Okay, thank you.